Hi, my name is Maya.
Hi, my name's Cam.
Hi, I'm Jasmine.
I'm Victor.
Hi, I'm Priscilla.
And we are Lab Group 76, the stressed salamanders.
We were presented with this value proposition and refined it through our user requirements. We quantified the user requirements through our engineering specifications.
We must repurpose as much of the current Canadian pipeline infrastructure as possible. The greenhouse gas emissions this energy system creates should be net zero. The energy produced should be equal to the current amount. The project must be fully completed by 2050, and the infrastructure should last around 50 years.
Any newly built infrastructure requires consultations from Indigenous communities within that area, and the jobs created must be equal to the jobs lost. The economic investment must be less than or equal to $100 per ton of greenhouse gas removed. Lastly, operation costs must be less than the revenue.
Canada has over 840,000 kilometers of pipelines. These graphs show that Canadians use a large portion of energy for space heating, mostly from natural gas or electricity. So our design creates clean electricity and hydrogen, a replacement for natural gas, to fill this need.
Although ammonia's energy density is lower than gasoline, ammonia as an energy source is far cheaper. Moreover, ammonia electrolysis is able to produce hydrogen, nitrogen, and electricity. Performing this process at low temperatures and low voltages can drastically increase the efficiency. Figure 6 represents the chemical equation of this process.
Hydrogen can be transported through pipelines alone or mixed with natural gas. This results in the mainstream use of hydrogen power for everyday appliances, where all incompatible appliances are adapted or replaced. Hydrogen combustion produces no greenhouse emissions, as demonstrated in Figure 7.
Our design is unique in that it has two energy carriers, ammonia and hydrogen. First of all, ammonia is collected from landfills, wastewater, and manure at ammonia collection sites. As this is fairly new technology, it will become more efficient and cost-effective over time. Ammonia is transported through petroleum pipelines to ammonia electrolysis sites, and both of these sites run on wind power.
Ammonia electrolysis further creates electricity, nitrogen, and hydrogen. The electricity is added to the grid. The nitrogen gas can be sold to third-party sellers, contributing to the economic return. It can alternatively be stored for future use, and the hydrogen is transported in natural gas pipelines and is then used for appliances as it will replace natural gas.
Next, we will move on to the analysis of our design. The initial construction period will be approximately 10 years. In this time, ammonia production and electrolysis sites will be built. All required pipelines will be relocated. All pipelines will be cleaned with chemical cleaning and pigging, and we will replace some components of pipelines, such as centrifugal compressors.
The transition period from end of construction until 2050. Hydrogen will be mixed into natural gas in increasing amounts. This will give people time to switch appliances that work with hydrogen. Ammonia collection and electrolysis will slowly ramp up, and the reduction of greenhouse gas emissions begins immediately once the blending process begins.
There will be negligible greenhouse gas emissions from the operation of the pipelines since ammonia electrolysis and hydrogen combustion create no emissions. The ammonia collection and electrolysis plants will be run by wind power, which also has no emissions. There will be emissions from construction and from the burning of natural gas during the transition period. However, these are far fewer than what is currently being produced.
Currently, natural gas and crude oil contribute approximately 17 quintillion joules of energy to Canada. However, through ammonia collection, this solution can produce approximately 300 quintillion joules. Furthermore, hydrogen transmission can carry between 80 to 98% as much energy as natural gas.
Ammonia is resistant to internal corrosion, so ammonia pipelines can operate for many decades. Hydrogen embrittlement is a significant concern. However, gradually increasing the percentage of hydrogen in the natural gas minimizes this. As a result, we determined that approximately 50 years of pipeline operation is reasonable.
Hydrogen will be transported in natural gas pipelines, whereas ammonia will be transported in petroleum pipelines. Therefore, the majority of existing pipeline infrastructure will be used and jobs will be maintained. There will be some movement of pipelines, but to reduce the amount, the same distribution grid will be used for hydrogen as is currently used for natural gas. Ammonia collection sites will be built at current petroleum extraction sites, and ammonia electrolysis plants will be built along current pipeline routes.
Hydrogen leaks out of pipeline less than natural gas. Hydrogen can explode and is odorless but could have additive like a natural gas. Ammonia has a very pungent smell, thus leaks can be detected easily. Ammonia released into the atmosphere is dangerous, and so by using it, we are increasing human and environmental safety.
The cost of ammonia stripping ranges from $1,100 to $1,800 per ton of ammonia. Ammonia electrolysis sites cost per ton about $2,100 to build and roughly $400 to maintain. Other costs that must be considered are the cleaning, relocating, and maintenance of pipelines, getting manure for the stripping plants, wind power setup, etc.
We estimate the total cost of this solution to be around $10 to $15 billion. The total investment required is estimated to be $70 per ton of carbon dioxide equivalent reduced.
In conclusion, our design concept collects ammonia stripped from manure, landfills, and wastewater, and further transports it through petroleum pipelines. It is then electrolyzed to create hydrogen that is then transported through natural gas pipelines.
There are net zero emissions as hydrogen combustion and ammonia electrolysis are carbon-free. The total amount of energy created is more than what the oil and gas sector currently produce. The construction period will end in 2050, and the total cost of the project is roughly $10 to $15 billion, with an investment of $70 per ton of carbon dioxide reduced.
Thank you for taking the time to listen to our presentation.